Let's look at type of batteries. There are two types of batteries that we are going to consider. That is primary batteries and secondary batteries. Okay, so primary batteries, these are non-rechargeable batteries. They can only be used once because the chemical reactions are irreversible. So examples of primary batteries include zinc carbon battery, alkaline battery, lithium primary battery, and silver oxide battery. Okay, then now we can look at the uses. What are some of the uses of these batteries? Okay, we find their use in remote controls. Of course, you don't recharge those batteries you use in remote controls. Okay. The second one, I think, also in wall clocks. Okay. Wall clocks. Then I think flashlights, and also calculators. Okay, so these use non-rechargeable batteries. Okay, then the other type of the batteries are secondary batteries. So these are rechargeable batteries. Okay, the second one is secondary batteries. So these are rechargeable. Okay, so secondary batteries, these are rechargeable batteries. These can be recharged and used many times. Okay, they can be recharged and used many times. Okay, they can be recharged and used many times because the chemical reactions are reversible. Okay, so examples includes the lead acid battery, the one used in the car. Okay, lead acid battery. We have nickel cadmium battery. Okay, then we also have nickel metal hydride battery. Nickel metal hydride battery. I think these are the most common ones. Okay, of course there are also others. Okay, so now let's look at the lead acid, since this one is the common battery that we all know. Okay, so the lead acid battery, we know it has this battery has 6 cells. Okay, so each cell produces 2 volts. Okay, so since the cells are 6, so it is now 6 times 2, which is giving us 12 volts. Okay, so this battery all these batteries, they have anode where oxidation occurs, okay, anode. Then there's also the cathode where reduction occurs, okay. So in this battery, the lead, so we're looking at lead acid battery, okay. So it produces a total voltage of 12 volts. Okay, so now let's look at the reaction that occurs at the anode. Okay, the anode reaction. So at the anode, we have the oxidation taking place. So the lead plus the acid used in this battery is sulfuric acid, okay, so which will give us the lead sulfate plus hydrogen ion plus the hydrogen ion, then plus the two electrons there, okay. So this is the reaction that occurs at the anode, the oxidation, okay. Then at the cathode, we have this reaction taking place. So the lead oxide plus hydrogen ions, then plus this one, then aqueous, then it plus the two electrons, then it will give us the lead sulfate plus water, lead sulfate plus water, okay. So this is the reaction that occurs at the anode, at the cathode, where the reduction occurs, okay. So these are the two reactions occurring in the lead acid battery, okay. So the electrolyte used is the sulfuric acid. This is the electrolyte used in this battery, okay. So the battery can be recharged. By external current, current, okay. So now once it's connected to the external current, what happens is the half reactions are reversed. Okay. Then some water is also decomposed. Some H2O is decomposed to hydrogen and oxygen, okay. And we have already mentioned that this battery has 6 cells, and each cell Each cell produces 2 volts, and in total the battery gives 12 volts. Okay, then what are some of the uses of these rechargeable batteries? So we can now look at the uses of rechargeable batteries. Number one, it's used in cars. Okay, we all know that cars use rechargeable batteries. Okay, used in cars. Okay, in cars. Then we also use rechargeable batteries in our laptops. Okay, laptops, mobile phones. Okay, then we also have solar energy storage systems. Solar energy storage systems. Okay, so all these uses rechargeable batteries. Okay, these are some of the thing. I mean, this is where the rechargeable batteries can be used in cars, laptops, mobile phones, solar energy storage systems. Okay, then we can also look at corrosion. Okay, corrosion. So let's quickly look at corrosion. Okay, so corrosion is a slow oxidation of a metal to form rust. Okay, slow oxidation of a metal to form rust. Okay, that is corrosion, the slow oxidation of a metal to form rust. Okay, so now how can we prevent or how do we know that the oxidation will take place? Okay, so now we can compare. We can use standard potential values. Okay, standard potential values can be used to determine whether a particular metal will undergo corrosion or not. Okay, then the standard potential, the reduction standard potential of oxygen, the reduction potential of oxygen is equal to 1.23 volts. 1.23 volts. This is the standard reduction potential for oxygen. Okay, so now all metals that have a standard potential lower than that of oxygen will undergo corrosion. Okay, so for example, we can look at let's compare the standard reduction potentials of some metals. Okay, the reduction potential for gold is 1.51 volts. Then for silver is 0.80 volts. Then for aluminium aluminium, that is negative 1.66 volts. Lead, Pb, that is negative 0.113 volts. Okay, then for iron is negative 0.0036 volts. Okay, we also have nickel, which is negative 0.23 volts. Okay, so these are the reduction potentials of these metals. So a metal with a standard potential lower than that of oxygen will be easily corroded. Okay, so from these we can see that so we compare. For oxygen is 1.23. Then I'll compare. So all these metals except gold have the reduction potentials lower than that of oxygen. Okay, so in this case it means gold will not corrode. Okay, then now in terms of arranging, you just look at the reduction potentials, comparing it with that of oxygen. So it means the one with the lowest will corrode faster. Okay, will corrode faster. Okay, so now you look at these. For aluminium, you can see aluminium, it's the lowest. Okay, aluminium is the lowest. So from this, aluminium the lowest, then the highest will be silver. Okay, we have removed gold already. Then now you can arrange those, comparing to that of oxygen. Okay, so that is corrosion. Then how can we protect corrosion or corrosion prevention? So let's look at some of the methods we can use for corrosion prevention. Corrosion prevention. Okay, so number one is painting or varnishing. Painting or varnishing. Painting or varnishing. Okay, so we can paint common structures like bridges or buildings. Okay, so that you can see that most of the bridges they are painted. So it's one way of preventing formation of rust. Okay, then we also have galvanization. Okay, galvanization, that is coating. So coating iron with steel or zinc. Coating iron with steel or zinc. So it's one way. Galvanized iron, I'm sure it means it has been coated. Since iron will easily corrode, so galvanization will form more like a shield outside. Okay, so it protects the iron inside. Okay, then we can also use electroplating. Electroplating is also one of them. Okay, electroplating. Okay, so coating metals coating metals. Coating metals, we can coat metals with chromium. Coating with metals such as chromium. Okay, coating metals with Cr, chromium, nickel, or tin. Okay, so coating with metals, chromium, nickel, or tin. Okay, that's the electroplating. Okay, but specifically for galvanization, we are using what? Steel or zinc. Then we can also use powder coating. Powder coating. This is a durable protective film. Durable protective finish. Okay, that's the powder coating. Okay, there's also cathodic protection. Okay, so this one prevent corrosion by making the metal act as a cathode. Okay, prevent corrosion by making a metal prevent corrosion by making the metal act. Prevent corrosion by making the metal act as a cathode. Okay, act as a cathode. Okay, so this is the method. Used to protect metals from corrosion. The ion to be protected is attached to another metal such as zinc or magnesium, which give up electrons easily. Okay, which gives electrons easily. Okay, which gives electrons easily up. It gives electrons easily. To oxygen than iron. Okay, so when we look at magnesium will give electrons much easily or readily than iron. When you look at the reactivity series of metals, you find that magnesium is more reactive than iron. Okay, so this is called sacrificial cathode. Okay, so the metal which is being coated outside, it's more like it's been sacrificed. Okay, since it will corrode, then leaving the iron inside safe. Okay, then we can also use corrosion inhibitors. Corrosion inhibitors can also be used to prevent corrosion inhibitors. So that's number 8 now. Corrosion inhibitors. So these are chemicals chemicals added to the environment to slow down. Chemicals added to the environment to slow down corrosion. Okay, so these are called corrosion inhibitors. Okay, examples include the phosphates, e.g. phosphates. We also have chromates and organic inhibitors. Okay, so these can be used in cooling systems, in boilers, also in pipelines. Okay, then we can also use alloying. Alloying is also one of them. Alloying. That is the formation of alloys. Okay, so we have stainless steel. We know that stainless steel contains chromium. Chromium. Okay, stainless steel contains chromium, which forms a protective oxide layer. It forms the protective oxide layer. Okay, that's alloying. Okay, we know that alloy is a mixture of metals. Okay, then we can also use there's also what we call environmental control. Okay, so here you just need to monitor. You can control humidity and temperatures. Control humidity and temperatures, and also store in a dry place. Okay, or dry place or environment. We know that a damp situation, if the humidity is high, it means corrosion will also be higher. Okay, so now we can now look at let's look at the stoichiometry. Let's look at the stoichiometry of electrolysis. Stoichiometry. Stoichiometry of electrolysis. Stoichiometry of electrolysis. First, we define electrolysis. Electrolysis is a process. By which an electric current is passed is passed through a substance to effect chemical change. Okay? Passed through, process by which an electric current is passed through a substance, to effect a chemical change. Okay, so a chemical change is one in which a substance, a chemical change that we are talking about here is one in which a substance will lose or gain electrons. That is a redox. Okay, a redox reaction. So electrolysis is carried out in an electrolytic cell. Okay, it is carried out in an electrolytic cell. So that is where it is carried out. Okay. So now we can calculate the mass. The mass deposited or liberated at the cathode. So the mass M, of a substance, liberated or deposited, the mass M of a substance liberated in electrolysis can be calculated by the formula. M, mass in grams. M is equal to QM over NF. QM over NF. Okay, so where M, uppercase M, is the molar mass. Molar mass in grams per mole. Molar mass in grams per mole. Then N is the number of moles of electrons. Number of moles of electrons. Moles of electrons involved in redox reaction at the electrode. Okay, number of moles of electrons involved in the redox reaction at the electrode. Then F is a Faraday. Constant. Faraday constant. F is a Faraday constant, which has a value 96,485 coulombs per mole electrons. That's the Faraday constant. Faraday constant. Then Q is the charge. Q is the charge. Charge is equal to current times time. Current times time. Time in seconds. Okay. Then using this formula, we can find the mass deposited at the cathode. Okay. Then the time should be in seconds. Okay. So Q is charge. So charge is equal to current times time in seconds, Current is measured in amps, then time in seconds. So amp times second will give us charge. Okay, charge. So Faraday's law of electrolysis states that amount of substance produced at each electrode. Amount of substance produced at each electrode is directly proportional to the quantity of charge flowing through the cell. Okay? Faraday's law of electrolysis. Faraday's law of electrolysis states that amount of substance are produced at each electrode. Produced at each electrode is directly proportional to the quantity of charge flowing through the cell. Okay, that is Faraday's law of electrolysis. Okay, so having done that, we can now look at an example. Let's see how we can perform some electrolysis problems. Okay, so example. A 40.0 amp current. A 40.0 amp current flowed through molten iron. Molten iron 3 chloride. Molten iron 3 chloride. Molten iron 3 chloride for 10 hours. For 10 hours. So determine the mass of iron. Determine the mass of iron and the volume of chlorine gas. And the volume of chlorine gas measured at measured at 25 degrees Celsius, measured at 25 degrees Celsius, and 1 atm. Okay, so this is the question. A 40.0 current flowed through molten iron 3 chloride for 10 hours. Determine the mass of iron and the volume of chlorine gas produced, measured at 25 degrees Celsius and 1 atm. Okay, so solution. So to solve this question, there are two ways we can use. Okay, so the first one, first of all, you need to write the half reactions at the anode and at the cathode. So we know at the anode, oxidation takes place. Then at the cathode, reduction. Okay, so there's a chloride ion. So chloride will form chlorine gas. This is oxidation taking place. Okay, so put a 2 there, then plus 2 electrons. Okay, so it's balanced. So that is oxidation. So you can see the increase in oxidation number from -1 to 0. It has increased. Okay, then reduction. This is, we are dealing with ion 3. Ion 3 plus 3 then gives us ion. Okay, so this is reduction. This is reduction. Okay, then now we can calculate the charge Q. Okay, so Q is equal to current times time. So our current in this case is 40 amps. Okay, so 40.0. okay, 40.0, that is the, okay, so 40 amps times time is 10 hours. So 10 hours times 3,600 seconds. So the time should be in seconds. So you convert 10 hours into seconds. Okay, so you know the conversion factor. Okay, so once you do that, you are going to get now 1.44 times 10 to the power 6 times 10 to the power 6 coulombs times 10 to the power 6 coulombs. So we have now calculated the charge. Okay, we have calculated the charge. Then we also know that 1 Faraday is equal to 1 more electron. 1 Faraday is equal to 1 more electron. Also know that 1 Faraday is equal to 96,485 coulombs per mole electrons. Okay, so using this relation, we can now convert coulombs to moles of electrons. Okay, so that is very straightforward to do. So we have now this is the coulombs that we have calculated here. So we want now to convert to moles of electrons. So what we do here, Or before we do that, we can convert, we can straight away convert coulombs to Faraday. Okay, so using this first relation, that 1 Faraday is equal to 1 more electrons, so we can convert Faraday to moles of electrons. So this is very straightforward to do. Okay, so we are now going to use this relation 1.44 times 10 to the power 6 coulombs. Okay, so 1.44 times 10 to the power 6 coulombs times 1 Faraday, which is coming from here. Okay, times 1 Faraday, then it over the Faraday constant 96,485 coulombs. So this one is now giving us so you can see that the coulombs will cancel. The coulombs will cancel, then which is now going to give us 4 point, you cancel the coulomb there, the coulomb and the coulomb. So we are now converting it into Faradays. Okay, so we are now going to get 4.9 moles. Here it is per mole electrons. So we are now getting 14.9 more electrons. Okay, more electrons. Now that we know that one Faraday is equal to 1 more electron. So what we have here is just the same as 14.9 more electrons. Okay, then now since we now know the moles of electrons, that is 14.9. Then now we are going to use the half reactions. The half reactions are given. Okay, so from what we have here, the mole ratio of electrons to ion, clearly you can see here it is what? It is 3 to 1. So we have 3 more electrons to 1 more ion. Okay, 3 to 1. So the mole ratio is 3 to 1. So since we know the number of moles of the electrons, so we can straight away do the calculations. So we have 14.9 moles of the electrons, then times 1 more ion over 3 moles of electrons. So we cancel the moles of electrons. Then 14.9, when you divide it by 3, you are now going to get 4.97 moles of ion. So if you know the moles of ion, clearly you can calculate the mass. Okay, since we know that mass, so mass of ion will equal to moles times molar mass. Okay, so the moles that we have is 4.97 moles. The molar mass of ion, that is 55.485 grams per mole. Okay, then now you multiply. When you multiply this number, you get 2 275.8 grams of iron. Okay, so this is the mass that is deposited at the cathode. Okay, so now we can also use the equation straight away. So let's see if we are going to find the same answer. So here we have found 275.8 grams. So now let's use the equation. We know that Q is equal to M. M is equal to QM over NF. Okay, so the Q we found the charge. Okay, so the charge calculated is 1.44 times 10 to the power 6 coulombs times molar mass of iron 55.485 grams per mole. This is the molar mass. Then over N. So N, the number of electrons at the electrode, in this case is cathode, that is 3. Okay, 3. Then times F, Faraday constant, 96.485 coulombs per mole electrons. Okay, so here we can see that the units will cancel the C there, the coulomb will cancel, then the moles of electrons cancels, and we are remaining with the grams there. Okay, so when you multiply the number on top and down, then you divide, you are going to find 275.8 grams of iron. Okay, so this is the mass of iron found. Even using, we can either use the half reactions or the equation straight away, we still find the same answer. Then we need now to calculate the volume of chlorine gas. The volume of chlorine gas produced. Okay, so since we know the moles of electrons are produced in the redox, so we now just compare. We can compare the mole ratio of chlorine gas to moles of electrons. So it's 1 to 2. Okay, so we have 14.9 moles of electrons, 14.9 moles of electrons, 14.9 moles of electrons. Okay, that's what we found, 14.9 moles of electrons. Then multiply by how many moles of chlorine. So we have 1 mole of chlorine from the equation. So the 1 mole is coming from here, 1 mole of chlorine. Then moles of electrons there is 2 moles. So 2 moles of electrons. So you cancel there, you cancel there. Okay. Then now we multiply. We multiply and divide by 2. So we are going to get 7.45 moles of chlorine. So now the gas at room temperature and 1 atm. So the volume of an ideal gas, that is 24 decimeter cubic per mole. Okay, then now volume of chlorine gas produced will equal to 7.45 moles times 24 decimeter cubic per mole. So you can see the per mole will go. Then the volume now will be 178.8. decimeter cubic. Okay, so that is how we carry out electrolysis calculations. Okay, then what are some of the applications? So in conclusion, let's now look at the applications of electrolysis. Applications of electrolysis. Applications of electrolysis. Number one, production of aluminium. Production of aluminium. Production of aluminium. Production of aluminium. Purification of metals. Purification of metals. Metal plating. Electrolysis of sodium. Electrolysis of sodium chloride. Production of chlorine. Production of chlorine and sodium hydroxide. So these are some of the applications of electrolysis. Okay. Anyway, there are so many examples on calculations. For today, we can end here. Then in the next video, we shall look at more examples and calculations on electrolysis. Thank you.